Hey, we are talking about the mean value theorem today. This is one of the most important theorems in calculus, not practically for calculation concern, but it's kind of the basis of a lot of our ability to prove the things in calculus. So if you go on in math, this will become a bigger and bigger theorem as you go. We are going to start actually with a different theorem called Rolle's theorem. And the reason we start with Rolle's theorem is that it's used to prove the mean value theorem, which we're not going to actually do. The proof is in the book if you'd like to see it, but we're going to start here. So the theorem says that let f be a continuous function, and you remember that the the let f be statement is kind of the if before the then. So these are the requirements. F has to be continuous. On a closed interval, we'll call it from A to B, and it has to be differentiable but it only has to be differentiable in the open interval, so not at the endpoints, okay? And f of A has to equal f of B. That means the values at the endpoints have to be equal. If all three of those conditions are met, then there exists at least one value C in the interval from A to B such that the derivative at C equals 0. Okay, so what this is saying in real person language right here is there has to be a max or a min. Okay, because that's what this f prime of c equals 0 is. It means the derivative is 0. That means there's a high or low point, critical point, and a max or a min. Okay, so let's draw a picture of this scenario, and so you can have a visual in your mind. We've got a function that does something. We know it's continuous. Okay, we also know it's differentiable everywhere on the interval, so nothing weird happening in the middle. Okay, and we also can see that the value of f of A equals f of B. The endpoints start and end at the same place. So this function that I've drawn fulfills all the requirements of Rolle's theorem. And we can see that there actually is a C value right here such that the derivative at that point is 0. It's a maximum. C is a critical point. Now, this says at least one. That means it's possible that there's more than one. So you could have a function. Let's draw it a little differently. Here's f of A and here's f of B, and say the function does something like this. All right, again, continuous, differentiable in the open interval. The f of A and f of B values are the same. And here we have actually two C values. One right here, we'll call it C1, where the derivative is 0, and one right here, we'll call it C2, where the derivative is also 0. You could have multiple, okay? It could zigzag up and down quite a bit. All right, so that is what Rolle's theorem says. And let's do a, what are we going to do? We're going to do a problem. So basically what Rolle's theorem says is if we start and we end in the same place, then what goes up has to come down. So like if you're going to go up at all, you're going to go down, you're going to create a max. That makes sense, I think. Okay, so we'll say verify this function on this interval 1 to 3 satisfies Rolle's theorem, and find all the points C guaranteed by that theorem. I am fairly certain I misspelled guaranteed. I am aware of that, but we're just going to continue. Okay, so this is kind of like our continuous function at a point problems that we did way back in chapter 2. You just basically have to verify the parts of the theorem. Continuous and differentiable is a little bit of a hand wave because we're going to assume that we are all aware that a parabola is continuous and differentiable. Okay, so all I'm going to do is state that. I think we're far enough along that we all can agree that parabolas are continuous. So f is continuous on an interval 1, 3. F is also differentiable. There's no points, there's no breaks in a parabola. Okay, so that's on one open interval 1, 3. The third thing that Rolle's theorem says is the endpoints have to have the same values. So this we actually have to check. So we're going to take a look at what f of 3 is. Okay, we plug in f of 3 and we get 2 times 9 minus 24 plus 6. That's going to equal 0, I think. Okay, and f of 1 is going to be 2 minus 8 plus 6, which is also 0. So f of 3 equals f of 1. Check. Okay? So therefore, by Rolle's theorem, that doesn't say theorem, there exists a C in this open interval from 1 to 3 such that f prime of C equals 0. So I'm using the shorthand that we talked about earlier, okay? There exists a C in 1 to 3. You do not have to use that shorthand, but if you choose, you end up writing it a lot, so there we go. So let's find that C. First of all, I'm going to calculate f prime of x because Rolle's theorem is talking about the derivative. So f prime of x is going to be 4x minus 8. And I want to know what that c value is that makes the derivative 0. So I'm going to plug 0 in for the derivative. Okay. I want to know what is that c value there. I'm going to add 8, divide by 4, and we can see that this actually happens at c equals 2. And because it was a linear equation, there is only one value. Okay, so that's a quick example of what a Rolle's theorem problem would look like. Let's move on to the mean value theorem and talk about what that says. It's very similar. Let f be continuous on this closed interval and differentiable on the open interval. Okay. Then there exists a c value in the interval a to b such that f prime of c equals f of b minus f of a all over b minus a. Okay, this formula right here is also sometimes written by just clearing the fractions. So you'll see it like this: f of b minus f of a equals f prime of c times b minus a. So basically you just took this equation right here and you multiplied both sides by b minus a to clear out the fractions. So don't be confused if you see something like this. It's saying the same thing as this, and you can write it either way you want. All right, so let's take a look at a picture for this guy. Turns out Rolle's theorem is actually just a special case of the mean value theorem. If you noticed, the mean value theorem does not have as many qualifications as Rolle's. It says that f has to be continuous and it has to be differentiable on these intervals, but it doesn't say that the endpoints have to be equal. Okay, so let's look at what that might look like. Here's your, let me do this in white. Here's your a value, and let's say your b is over here, and they are different. See, they map over to different y values. So here's my function. Whoop, let me try that again. Okay, something like this going on. This right here is the slope formula. Okay, if you notice, that's the y minus y over x minus x. So it's just saying, hey, here's the slope between the endpoints. Okay, this red line is the f of b minus f of a over b minus a. That's your slope value between the 2 points a and b. And all of this mean value theorem is saying somewhere in this function there's an equal slope at a tangent point. Okay, so like on this picture, I can see that, well, let's see, maybe right there is going to have, well, I don't know, close to an equal. We'll pretend like that's pretty close. Okay, that tangent line right there has an equal slope. Okay, also there is also a point right here where that tangent line is going to have the same slope. So these are the c values that the mean value theorem is saying. So whereas Rolle's theorem pulled the endpoints equal and found a min and a max, the mean value theorem is just finding the points C1 and C2 where you have the same slope as your endpoints slope, right? The problems look really similar. You're going to verify and then find these values. So let's walk through one of them. For f of x equals x cubed plus 2x plus 1 on this interval closed from 0 to 6, determine if the mean value theorem applies. We use MVT for mean value theorem, and if it does, find the C value that satisfies the theorem. All right, so we'll go through this step. First, the two qualifications for mean value theorem are just continuous differentiable. Well, this is a cubic, okay? Every polynomial is differentiable and continuous on the entire domain. So, and you can assume that is true. So I'm going to say f of x is continuous on 0, 6, and f of x is differentiable on the open interval 0 to 6. So those are my two qualifications. They are clearly true. So I say, therefore, the mean value theorem applies, and we are going to find that C value. Now, the mean value theorem says take the derivative, okay, and set it equal to the slope at the endpoints. Okay, so let's do that. Here's the derivative. Okay, and let's find the slope at the endpoints. F of b minus f of a over b minus a. So that's going to be f of 6 minus f of 0, our specific endpoints here, over 6 minus 0. So f of 6 is going to be, it ends up being, if my calculations are right, it's 229. So what I'm doing is I'm taking 6 and I'm plugging it into this original function up here. So 6 cubed plus 12 plus 1, and then minus, plug in 0, and you get 1 over 6 minus 0, and this ends up being 38. So what this is saying is, if we were to draw a picture of this, I don't know offhand what the function looks like, although it would be a great thing to just go on Class Calc and graph it. If you're looking at between 0 here and 3, 6 right here, the value at 6 is up here at, we'll call this 229, and the value at 0 is 1 here, and it's doing something in the middle. You know, it's, I don't know what it's doing, okay, but it's somehow continuous and differentiable through those 2 points, and we're trying to find the slope between these 2 points right here is 38. Okay, that's what this is calculating, is the slope of that line that connects the endpoints. And we want to know where in this interval here is the slope equal to 38. Okay, well, the derivative finds the slope. So we're going to say, I want to know where is this derivative equal to 38. So I just set that as equal. That's what the theorem says to do. It's saying take the derivative and set it equal to your slope. All right, and then I go ahead and solve this. I get it's a quadratic, so I need to get everything over on one side. I'm going to subtract over that 38. Or no, let's see. Sorry. It's just a squared term, so I don't have to run a quadratic. Just subtract the 2. Okay. Oh goodness, I'm going into typo land really fast here. I'm going to get it together. Divide by 3 is 12. So x is going to be plus or minus the square root of 12, which is, that reduces to 2 root 3. Okay, I do want you to reduce roots. Again, trying to get you just more and more attention to detail as we go on in our progression of math classes. Okay, now there's 2 solutions, okay, because there always is when you root both sides, you get a plus or minus, but our interval is from 0 to 6. So negative 2 root 3 is not in this interval from 0 to 6, okay, and so our C value that we get is just going to be 2 root 3, positive 2 root 3, and that's your value. So 2 root 3 is like, I don't know, it's like somewhere in here, it's close to 3 plus or minus a little bit estimation. So somewhere in here, what it's saying is the slope of the tangent line of this graph, whatever it looks like, is going to be the same as that red line. That's the idea. Okay, let's see what happens and how you handle the write-up if something doesn't meet the mean value theorem. Okay, so let's look at this example. For f of x equals x squared plus 3x plus 2 over x on the interval negative 1 to 1, determine if the mean value theorem applies. If it does, find the C. Okay, so same directions, same plan. But in this situation, you'd look and say, hey, f has a domain problem. The domain on f of x is that x can't equal 0. Because, and just for review, okay, here's things that have problems. Roots have problems. They can't be negative. You can't root a negative. So they're going to have a domain problem. Logs have problems. You can't log 0 or a negative. And fractions have problems because the bottom of fractions can't be 0. We did this domain stuff in pre-calc pretty heavily, so hopefully you remember that. And so I can say f of x domain says that x can't be 0. And 0 is in this interval from -1 to 1. Okay, so f is not continuous on -1 to 1. And so the mean value theorem, mean value theorem does not apply. So that's kind of what the write-up looks like. You state where there's a problem and what requirement it's violating, and then and that's all. That's all you do. And if you remember what these guys look like, these are rational functions. This probably has either a vertical asymptote at 0, and it's doing some kind of, I don't know, some kind of swooshy thing, or it has a hole at 0, one of the two, depending on how that graphs out. And so this is not going to be continuous from -1 to 1. There's going to be a break, and it's not going to be differentiable either. All right, that is it for this section. Just getting used to some little simple proofs, and I'll see you next time.